Section 7.3 Part 1 is all about volumes. Um, and it's about volumes using a particular technique called slicing. And I'm going to start off very quickly with some pictures I've drawn. You don't need to take notes until we actually hit the printed notes. But just to give some context to this, you already know how to find the volume of the two shapes on the left-hand side. You already know that the volume of a box is given by length times width times height, a rectangular box. And the length times the width is the base area. So it's going to be the base area, length times width, times height. Easy peasy, you've known that for years. I've got a cylindrical can, maybe a can of soup here. What's the volume of that? We've also done that in the past. The volume is equal to the base area, which is pi r squared, times the height. The important thing though, it's the base area times the height. But what do you do if you want to find the volume of a football? Or the right-hand side represents maybe a vase that your little cousin made at a pottery class, and it's kind of this lumpy, misshapen mess. How do you find areas of those two shapes? Well, the easy areas on the left-hand side were easy because of a characteristic that these two solids on the left-hand side have. We say their cross sections are all the same. Now, what do I mean by cross sections? It's important that you understand that for this whole section. If you look at the box and the cylinder, and I've drawn them so that they're sitting with their bases are on a horizontal surface, a nice flat horizontal surface. And then imagine just making slices horizontally. So let's make a slice near the bottom, a horizontal slice of the box, and I'll get a shape that is a rectangle. And if I make it nearer the top, not only will I get a rectangle for my, what I call my cross section, but it's going to be exactly the same size and shape as either the base or the top. Similarly, for my cylindrical can, if I make, if it's sitting with this base horizontally, every time I kind of slice horizontally, I get a circle. And not only is it a circle the same as the top and the bottom, it's exactly the same size as the top and the bottom. The cross sections are all the same. And that's what enables us to come up with a simple volume formula. If you look at my football, if I slice horizontally, I'll probably get some sort of oval shapes, won't I, maybe? I'm trying to remember what a football kind of looks like if I slice it. But if I slice near the top or in the middle, I'm going to get maybe the same shape, but definitely a different size. Similarly, if I were to slice vertically, I probably would get something that's closer to a circle. But again, depending where I slice, make my vertical slices, they may be the same shape, but they're going to definitely be different sizes. And as for the artwork that your cousin made, that's even worse because, depending where it's standing on a horizontal base, but if I make my slices horizontal, they not only might be different sizes, but they might actually be kind of really different shapes too. So how do we cope with that? Well, what we do is we make very skinny slices. So we're going to have a look at the actual notes. And before we start those, we're going to talk about a little bit of vocabulary. What we call a cylinder further up the page is actually a right circular cylinder. It's a circular cylinder because each cross section is a circle. But also, if the axis, the line segment that joins the centers of the top and the bottom, is perpendicular at right angles to both the base and the top. So that's a right circular cylinder. We can generalize this to just a right cylinder. Now, the difference between a right cylinder and a right circular cylinder is that the cross sections aren't circular. So you can see the top and the bottom. If the bottom is sitting on a horizontal base, then to be a right cylinder, that top also has to be just exactly vertically above it. And when I make my cross sections, a horizontal cut, what will happen is the cross sections won't be circles, but they'll be exactly the same size and shape as either the top or the bottom. And because of that property, where all the cross sections, if the base is horizontal and all the cross sections is exactly the same as the base or the top, then the volume will be the base area times the height. And this is what we use if we have a general shape, maybe not your cousin's artwork, but an arbitrary solid shape, which actually I always think looks a little bit like a dog bone. All right, if I have a dog bone, right, and I take my slices, the slices are going to kind of be different sizes and shapes depending on where I make my my cross sections. Here, it looks like I'm sort of making vertical cross sections, and the cross-sectional area will depend where you are from some measuring point. It'll be a function of that distance. So if we look at our diagram here, we've got a measuring point O, and I've got an x-axis. And I've drawn one of these very thin cross-sectional slices. And by making it very thin, I'm actually creating a right cylinder. And the area of my cross-sectional slice, it's a function of x. It's a function of how far down the dog bone I am. So here's my dog bone. The ends of the dog bone are at x equals a and x equals b. And I've created this slice, which I've magnified to show that I've created a right cylinder. And the notation is I've sandwiched it between x sub k minus 1 and x sub k, and the thickness is going to be delta x sub k, so that's like the height of my cylinder. The area, which would be my base area, is a function of the x value, which is x sub k. So applying my base area times the height or the thickness, it's going to be base area times the height or the thickness is delta x sub k. And then if I want the volume of the whole solid, I just add up all those slices and I put in my sigma sign, and we've got a Riemann sum. And we take, to get the overall exact volume, I'm going to take the limit as delta x goes to 0, and you know what that creates. It creates a definite integral. The delta x sub k morphs into a dx. I drop the x sub k and I just write a of x. And then since the x values, the dog bone was between x is a and x is b, those are my limits of the integration. So volume of a solid, here is the very nifty formula that we're going to use all in part 1 of 7.3. The volume of a solid of known integrable cross-section area, a of x from x of a to x of b, is given by this. Integrable means, well, you will be able to do it an integral, even if you have to use a calculator. The tricky bit is known. Usually you don't start off knowing it, you have to find it, and that's where the work is. It's finding the formula for the cross section as a function of x. Here are the steps we're going to go through as we find volumes by slices. Sketch diagram, always do a diagram, in fact we often do two, with a typical cross section, and very important, mark on the relevant coordinates. As we do particularly part 3, it really makes a big difference writing on the coordinates. Finding the formula for a of x, establishing the limits of integration, and then actually integrating, finding the definite integral. WRT, I think we've already talked about that. It means with respect to x. All right? So let's quickly see if we can zip through a problem. Find the volume of the following solid. The cross section is perpendicular to the x-axis. So my cross sections are going to be perpendicular to the x-axis, and they run from the semicircle y is negative root 1 minus x to the semicircle y is positive root of 1 minus x, sorry, 1 minus x squared, I misspoke. Let's quickly just review that. Remember, if you have y is plus or minus the square root of 1 minus x squared, that comes exactly from y squared is 1 minus x squared, as if you solve that, and that's x squared plus y squared equals 1. And if I write it like that, you immediately recognize that as a circle, center of the origin, radius 1. Now you'll notice there are two diagrams for this, because one of them is trying to give a 3D picture of what's going on, and the other is just looking down on what we call the XY plane. Here, I'll just quickly look at the lower diagram. It's the whole circle, x squared plus y squared is 1. The top graph is y is the positive root of 1 minus x squared. The bottom graph is y is the bottom half of it is y is the negative root of 1 minus x squared, and its radius is 1, so these 2 points on the x-axis are negative 1, 0, 1, 0. Okay, so that's looking at it, looking down at my diagram. I'm trying to get a three-dimensional picture of what's going on. I know that the bases of my cross-section are perpendicular. So here's one of my bases, perpendicular to the x-axis. Perpendicular x-axis means parallel y-axis. So the green segment represents the base of one of my cross sections, and then trying to give a three-dimensional look to it, I've kind of had to slant my y-axis, and I've drawn in 4 squares that are my cross section. And if we call the points P, Q, here would be, this is P, Q on my three-dimensional picture. Okay? In fact, I can do a little bit better than that. Let's go and reset this. What I've got here is a circle. All right? We can show a lot of chords. Remember, chords join points on the circle. All those chords are perpendicular to the x-axis. I'm going to drop my y-axis flatter so to give a three-dimensional look. And I'm going to just create 4 of my cross sections. Can you see there are 4 squares whose bases are perpendicular to the x-axis? And those are my cross sections. Now, let's see what the actual solid looks like. You know, most people have a lot of trouble imagining what the solid looks like, and don't worry about that, because actually you can find the volume without even being able to visualize it. So let's just see what the final solid looks like. Here are the 4 cross sections in it. If I were to just take one square and put it in different positions, you can see it changes area as it's in different positions. I'm going to stop it right there. Oh, curses, too late. Well, I was going to try, I'm going to stop it so that it corresponds with the cross section that I'm going to work with. All right, there's a cross section there. And where I've got y1 and y2 in this diagram, I've called P and Q on our diagram. So let's go back to our notes. I'm only going to take one of my cross sections, and you can see it's a square that has thickness, and the thickness is in the x direction, and it's going to be delta x, because x goes this way, and so the thickness of my cross section is delta x. So if I can make that a little thicker, all right, You know, this would be, that's delta x thick. Now, I'm going to use my formula that is going to be the basis of this whole section. The volume is going to be equal to the integral of the area of the cross-section function of x dx. And let's see my limits. They're going to go from x's start at -1, finish at 1. You'll see that if I go back to this one very quickly, quick, drop that. Let's sweep one of my squares. You can see it starts on the extreme left with an x of whatever that is on the extreme left, and then it finishes up on the extreme right. So going back to our notes, the x's start at -1 and they finish at +1. So I'm going to go from -1 to 1. And the only thing left now is to come up with the area of the square. The area of my cross section here. Can I figure it out? Well, I know how to find the area of a square. It's a side times a side. So all I need to do is to write down what is the side of my cross section, which is a square. And that's going to be the same as PQ. That's the side. And in order to find PQ, remember I said it's really helpful to write down the coordinates. If you look at P and Q, they both share the same x coordinates, but their y coordinates are different. What's a y coordinate of P? Oh, it's on y equals positive root of 1 minus x squared. And the y coordinate of Q is the negative of that. And when you have 2 points vertically above each other, their length is going to be the difference of their y's, the top y minus the bottom y. The top y minus the bottom y. And those two negatives give me a plus. So that's what PQ is. And then for A of x, which is the area of my square, is going to be equal to 2 times root 1 minus x squared. That's the base of the square, height of the square. Overall, I'm going to get 4, and the square roots combine to give me 1 minus x squared. So my volume is simply going to be -1 to 1. 4 times 1 minus x squared dx. 4 is a constant multiplier. We can take it out if we wish. And I'm left to anti-differentiate 1 minus x squared, which hopefully you can do in your sleep. Put in the limits and you are done.